Uh, Hello, Professor. Here is the demonstration of my final year project, and my final year project title is Move and Charge System for AGVS. And the system has six main components: the receiving coils, the transmitting coils, and these two are the inverter, and this is the DSP chip for PWM control, and this is the rectifier. This is the power supply, and this is the load. And we connect uh, all these six components, and we have four channels for oscillator. And the first one is for the input voltage of the system, and the second is the uh, current in the transmitting coils, and the third is the output voltage of the system, and the last is the output current of the receiving coils. And we will build a program into the DSP chip to generate the PWM control and to control the inverter. And the power will slide from power supply to the inverter, and the inverter will convert the DC into AC, and to the transmitting coil for coupling, magnet for coupling. And the receiver coils will generate the output current to the rectifier, and the rectifier will convert the AC back to DC for the load. And this tool is the LCC compensation work for boost the current in coupling process. And we are fixed the high at 6 cm in this situation, and our input voltage is 25 volt, and the input current is 2.34 ampere. And you can see now at the fix of high of 6 centimeter, and the input is 25 volt, and we can get the output is about 55.56 watts. And this the receiver coils is placed at the center of two transmitting coils. And next we will move the receiving coils. And at this situation, we move the receiving coils at the edge. We define it as negative 15 centimeter. And at this time, the output power is about 8 watts. And next we will move it to the positive 15 centimeter. And at this situation, the receiving coil is also at the edge of the track. We define it as positive 15 centimeter. And you can see the power of this situation is 8.22 watts, and it is very close to the negative 15 centimeter. And now we can increase the input voltage of this system. And now the input voltage is 30 volts, and the output power is 12.07 watts, and there is a small increase of the efficiency after you calculation it. Now I move the receiver coils quickly to the right from the center to the positive 15 centimeter, and now repeat. And we can see in the oscillator the power is dramatically decreased in this situation. Hello, Professor. My name is Liu Haitian, and today I'm going to present my final year project. Work on a move and charge system for automatic guided vehicles. There is a dynamic wireless power transfer system that allows AGVs to charge continuously while they are moving. And let me start with the motivation. AGVs are the backbone of modern smart manufacturing, logistics, and warehouse automation. Their continuous operation is absolutely critical. For conventional factory charging ports, these vehicles should stop working while they are recharged. that interrupt workflows, limit operational range, and mechanical docking station at wear and failure points. So the idea behind this project is simple. Embed wireless power transport coils into the flow track and let the HV charge and move, with no physical contact, no downtime, and no maintenance issue. Now let me give you a quick overview of the system architecture. We start with the DC power supply, that is the full bridge inverter, which converts DC into a high-frequency AC square wave. Then an LCC compensation network drives the transmitter coil. On the HV side, a receiver coil picks up the magnetic field, and a rectifier converts to backplate labeled DC to charge the battery. The key here is that we use two transmitter coils instead of one. That way, as the AGV moves along the track, there is always good coupling coverage. And let me show you the actual hardware. The system has six main parts. There are two circular transmitter coils made of liquid wire, flush mounting in the track. The receiver coil is the oblong shape, but also liquid wire, mounting under the AGV. The LCC network, the PWM controller, the full bridge inverter, and the rectifier are all customer built. The inverter uses two ASV A5110 half-bridge gate driver ICs, and the whole system is controlled by a DSP chip running at 200 MHz. We did careful coil characterization, and the transmitter coils are circular ring with an inner diameter of 5 cm and the outer diameter of 15 cm. The receiver is a rounded rectangular with a maximum lateral span of 30 cm. When we measure self-inductance versus horizontal position, each transmitter coil sits at about 20 newtons near a 5 cm offset, and at the center the two curves cross over nicely, show good symmetry of the system. For vertical height from 2 cm to 10 cm, all inductance drop automatically. That tells us that keeping a small air gap is really important in a real application. Mutual inductance and coupling coefficient follow the same trend. The left transmitter has higher mutual inductance on the negative side, the right one on the positive side, and the intersect at the center. That overlapping coverage window is exactly what we want to maintain continuous power delivery as the HV moves. Now the LTP compensation network. This is the heart of the system misalignment tolerance. On the primary side, we add a series inductor and two capacitors. The network of the transmitter core current is stay nearly constant, regardless of load or coupling variation. We also switch in harmonics, which improves electromagnetic compatibility. The design equation ensures resonance at the switching frequency and constant current behavior. So power transfer is minimized even when the receiver is not perfectly aligned. And let's talk about the inverter and the PWM control. The inverter converts the DC supply into 200 kHz square wave. We choose a full bridge system to get the maximum voltage swing across the coil. The two AGV A5110 half-bridge ICS form the full bridge, and the PCB layout follows the datasheet recommendation closely, with spark capacitance and high-frequency bypass inhibitors placed right next to the spin nodes to minimize parasite ringing. All the PWM control come from the DSP enhanced PWM procedure. We use two ePWM modules in a master slave configuration. ePWM1 is the master. It generates the sample to faithful complementary output on channels A and B, and it sends a synchronization signal to the slave. ePWM2 receives that synchronization signal and applies a 180-degree phase shift using the TDPSS register. That gives us the second half of the full bridge drive. We also invert 200 nanoseconds of the dead time between the high side and low side gate signal to prevent short through color. As a nice visual check, onboard LED toggles at 1 Hz, so we can see that the interrupter routing is running correctly. The interrupter routine executes every PWM period. It updates the control register and calculate the requirement feature in real time. In up-down count mode, the CMPA register set the duty circle and the phase formula is shift equal phase shift angle times switching frequency divided by 2 pi times inverter frequency. For 180 degree shift, that gives exactly 215 timer counts, so EPWM2 less EPWM1 by half a switching period. And now for the experimental result, we fix the vertical height between transmitter and receiver at 6 centimeters, and we switch the receiver laterally along the track. The horizontal 0.65 is at the midpoint between the two transmitter coils. At each position, we record 4 channels at the same time. And the black is the input DC voltage, and the blue is the transmitter coil current, and the red is the output DC voltage, and the green is the receiver coil current. At the H position, say minus 15 centimeter, coupling the output voltage drops and the efficiency falls significantly, while at the center position 0 centimeter, both transmitter coils contribute symmetrically. Output voltage peaks and the efficiency exceeds 89%. The oscilloscope shows clearly show that when the AGV is centered, the waveforms are strong and clear. And we also connect quantity efficiency data of 3 actual position and 2 input voltage level. At 24.9 volts input and center alignment, the efficiency is 89.39% at the same voltage but at minus 16 centimeter, we drop to about 57%. And at plus 15 centimeter, about 51%, but when we increase input to 30 volts at center alignment, efficiency reached 91.37%. This is our peak, so not only does center alignment give the best performance, but higher input power also improve efficiency because of conduction losses. So what have we concluded? 4 main points. First, electro misalignment significantly affect all parameters, but the few transmitter systems they are through symmetric coverage. Second, vertical high degrees everything. Self-inductance, neutral inductance, and coupling coefficient all drop as the ALK increases. That means mechanical tolerance zero matter. The input power level influence transfer efficiency. Higher power gives higher efficiency within the practical range. And fourth, we now have a complement set of experiment data that provides a solid foundation for future optimization. Looking ahead, there are 4 directions I want to pursue. One, coil shape and material optimization. We can try circular square or DD coils and add very close to boost coupling. To refine the compensation network, maybe try access or other LTC variants to boost efficiency beyond 91% over a wider alignment range. They build multi-coil array structure with intelligent activation switches, so the charging zone becomes even larger and the hard over between coils is seamless. And fourth, develop higher fidelity electromagnetic simulation in Narcisse Maxwell or console to cross-validate our measurement and speed up design iteration before we build physical prototypes. And this all for the presentation of my final year project.